All right, there we go. A little bit of camera issue at the beginning. I hope everybody's doing well. Good morning, everybody. I just want to start by, let me just get all my stuff ready over here. I'm going to start by sharing my screen. I want to showcase kind of where we're at, what we're in the middle of, all that fun stuff. We started last time on section 11.8, and we had finished out 11.6. We don't lecture on 11.7, and like I said, we started on 11.8. And then I think I'm almost certain I mentioned it last time, that I went through and I added the videos to all of the chapter 11 material, so you can see within these that there are now all the prerequisite videos, these are things that normally people wouldn't watch unless they need to review something like L'Hopital's rule or factorials or limit laws or something like that. So that was from 11.1. And then there's core lecture videos that we did in class, and then links to the Wolfram demonstrations that I might have used during lecture. And then the lecture notes themselves are just the regular lecture notes. Just to give you a heads up. And I did the same thing. For example, we are just at the beginnings. Actually, we're almost through section 11.8. I put the video up from Wednesday, and there was a Wolfram demonstrations applet that I had embedded in my lecture notes that you're more than welcome to take a look at, but actually Desmos works a lot better for that. And then of course my lecture notes are right there. So that all being said, let's go ahead and dive into, if I can. There we go. The lecture. And I have to actually go to section 11.8. I just had uploaded 11.9. So to remind you of last time, kind of an exciting section, in my opinion, a really neat topic within mathematics. Power series, and this introduces the ability for us to take a function that we would not be able to work with and possibly convert it to a power series. We don't know how to convert it just yet, so this is a heads up. We don't know how to convert any given function into a power series. So right now, all we're doing is just playing with given power series. So somebody hands us a summation that involves x now, and they hand us also the coefficients of that summation. That's what all of this notation is. Let me go ahead and point at things. So there's the coefficient of the nth power of x, and we say that the power series, because x minus a, the power series is centered at a. That's what we'd say. Often, excuse me, we'll deal with power series just centered at 0. So it'll be x to the nth, not x minus a, but just x to the nth. That's technically x minus 0, so it's centered at 0. However, there will be times when we center elsewhere that actually ends up being somewhat important. And when you expand a power series off to the right there, you see that we did that last time. You get this infinitely long polynomial representation of this power series. And as we started playing with Desmos last time to showcase that, hey, take a look, e to the x is approximated by this infinitely long polynomial that we played with last time, and we'll see something like that today, so don't worry. We found that given functions, or functions that we're used to, could possibly be represented by infinitely long polynomials. It's actually true that almost every single, sorry, I'm moving the light here. Every single every single function that we've been handed in the past, almost all of them, can be represented by power series. There are some non-elementary functions that do not have power series representations. These would be things like functions that have kinks, corners, or cusps. So a function that might look like that, or any type of absolute value function, those tend to not have power series representations. And the main reason why is because they just don't have an infinite number of derivatives. That's not going to be important for today, but I'm just letting you know that that's actually the reason why some functions just don't have power series representations. So again, today we are just continuing our conversation. If somebody hands me a power series, the very first elementary question is, when will that power series converge? That's it. So for right now, somebody walks in the room and they hand me a power series and they say, I just need to know, when will that converge? And so if we fast forward a little bit, I'll erase this because that was kind of the big reveal, but we had this power series. It's a function of x, a series that is a function of x. And we were asked, what is the radius and the interval, or what are the radius and interval of convergence? And we basically, those are fancy ways, at least the interval of convergence is a fancy way of saying, hey, for what x values can I guarantee this will converge? And the way we go about that often when you deal with power series is via the ratio test or the root test. In this case, because this series is not all being raised to the nth power, a good idea is probably the ratio test. So we did the ratio test here. And so notice that I rewrote x to the nth over n factorial's x minus 0 to the nth, just to showcase that it is very much of the form x minus a to the nth times some constant. That's the only reason why I wrote that x minus 0 to the nth. But to be very honest with you, you would never write that. You would just leave it as x to the nth over n factorial. So they hand me that series, and I just want to know, hey, for what x values will that converge? I expanded that out just to showcase what that series looks like because, well, it's kind of nice to see. And how do you find that radius or interval of convergence? Well, you just have to find out when the series converges. And so the ratio test is a beautiful test to use. You guys are in the middle of using it. I think that you, that homework on that section, well, it's due next week, next Monday. But still, you're probably already working on it. And so you're used to seeing this notation, a limit as n goes to infinity of the absolute value of the n plus first term of your series divided by the nth term of your series. In this case, for our power series they handed us, the n plus first term is this guy. That's a sub n plus 1. And the reciprocal, it's terrible, plus 1. The reciprocal of the nth term, I should probably point the arrow slightly differently. There we go. The reciprocal of the nth term is that guy right there. So again, it's the n plus first term divided by the nth term, but I like to write it as the n plus first term times the reciprocal of the nth term. And I'm not alone in that. Most people do like to do that. It's just a lot easier. In this case, this is very different or somewhat different than 11.6, which was the ratio and root test, in that when you're working with series in 11.6, you didn't have unknowns. You didn't have x's. You had n's, but that's okay. But you didn't have x's. The fact that you have x's here introduces a level of an unknown. And so when you do your mathematics here, you're going to end up with, get a highlighter, a factor involving that x. You can ignore this 27 million for right now. And that factor involving x usually can just be factored out of the limit eventually. So you have that factor of x times the limit. And remember, you want, for convergence, I'll write this over here, we want this limit to be less than 1, because that would give us a guaranteed convergence for our series, right? That's the whole ratio test, is that you want the result of your limit process, this guy right here, to be less than 1. But what we found was, no matter what the value of x is, that limit right there is going to tend to 0, and 0 times whatever x is still 0. And so that will always be less than 1. And a great way to say that is literally to say that limit will always be less than 1. So when will our series converge? It will always converge because you use the word always. So our series will always converge no matter what the value of x is. So therefore, our radius, or I'm sorry, interval of convergence is any x value you want. So from negative infinity to positive infinity. And that's what we wrote down here. The power series converges always. So for negative infinity to positive infinity, it converges. And the radius of convergence, well, from center, which is, we'll just say 0, to the right or left edge, well, that is going to be infinity, right? That's the radius of that interval. And we demonstrated this using Desmos last class. Maybe I'll go ahead and just showcase that here, just to get us all on the same mindset. There's a lot of buildup here, by the way. So I hope you don't mind that I'm taking my time kind of talking about this. It's mainly because I think that it's very useful to spend a few moments rehashing this material. It's incredibly important material. So let's say that we have that power function, or that power series, sorry, g of x is equal to, and then it was the sum from n equals, I think it was just 0, n equals 0 to some value. I'm going to stop it at a value of a because I have a slider up above that. And it was x to the nth, typing with one hand, sorry, divided by n factorial. There we go. Now you can see, and by the way, I should also graph y equals e to the x because that's actually what it's going to converge to. You can see right now that, there we go, that purple line is just there because I'm summing up the series from 0 to a equals 0. But if I start moving a to 1, and then to 2, 3, 4, 5, and so on and so forth, you can see that our purple line there, or not line, but our purple curve is really locking itself to e to the x. As we increase the upper limit, which is a, we see that it extends further out to the left. It's actually extending further out to the right as well. It's just, it rises so quickly you can't tell. But the more terms I add to the series, the wider my interval gets as far as how long it links up to e to the x. And so if I were to add terms forever, like out to infinity, which I'm not going to do here because Desmos cannot handle that, but if I were to add terms out to very large numbers, you'll see that it continually locks down, gets wider and wider, and locks for a longer period of time. So this is a great justification that the interval of convergence, how far out from the center of this is at 0. How far out from that 0 can I guarantee I have a link to e to the x if I keep adding terms? Well, it's as far out as you want. As long as you keep adding terms, it'll keep widening the interval of convergence. Now, is it going to be the case that every function is equivalent to its infinite power series? No, it is not the case. And we'll see that in a little bit. But for right now, at least e to the x seems to link up very nicely to the summation from 0 to infinity of x to the n over n factorial. That was what we dealt with last time. Let me hop back to my get this going. There's not a fast way for me to switch between my laptop and my desktop. Sorry about that. All right. So that's just a visual reminder of what an interval of convergence is. Raise this up as well. Okay. So then we mentioned something here, and I want to actually clarify this. So obviously, if x is equal to a, then the power series will converge. It'll converge to c naught, actually. But there was a piece of advice down here. If the original series is geometric, then the interval of convergence will not include the endpoints. It's very, very rare that your original series, your original power series, is geometric. So that's just a heads up that it's likely not the case that you're going to be handed a geometric power series. So I do need to I just want to drive that point home. So I'll put this as a warning. We will have to check the endpoints. When finding intervals of convergence. It's just a reality. Mainly because if you're not dealing with a geometric power series, which is incredibly rare that you get to deal with one. So you might as well just assume you're not. If you're not dealing with a geometric power series, then it could be the case that you have divergence at one edge of your interval of convergence and convergence on the other edge. We'll talk about that when we see an example like that. We will see a lot of examples like that. So don't be too concerned about that. So then we went into this example and we said, okay, here's a power series. It's centered at 2. We did the root test in this case because everything was raised to the nth power. And we found that it was always, when you run the root test, always less than 0. And again, the interval of convergence was infinite, negative infinity to positive infinity. So the radius of convergence is infinite. There's no need to check endpoints there because you can't check infinity. So that was our second example. But then where we left off, and I think that's where we're starting now, is example 3. Find the radius and the interval of convergence of this power series. Again, not everything was raised to the nth power, so I'm not going to use a root test. I'll use a ratio test. So we used a ratio test. We did the n plus first term of our series. And we multiplied that by the reciprocal of the nth term of our series. And we started canceling things out because they cancel beautifully. Again, when you're dealing with power series and you're doing the ratio test or the root test, that factor involving x will be able to be pulled outside of the limit. Excuse me. However, when you do that, remember, it was within an absolute value. So you will have absolute values of that factor coming out. I have to clear my throat. I'm going to mute. Well, we'll see. That didn't help at all. Excuse me. I don't know what's going on. All right. That sounds a little bit better. Okay. So we factored out the absolute value of x minus 2. We still had that limit going on, but that limit's actually pretty easy to evaluate. We dealt with calculus now for almost a full year. And so as n goes to infinity, we know that's going to be 1 because, again, it's a second degree polynomial over a second degree polynomial. Lead coefficients are 1, so it limits to 1 over 1, which is 1. Now remember, we want this to be less than 1. Okay, great. So that will be kind of our condition. Like we're trying to find for what x values will that power series converge. It'll converge if the absolute value of x minus 2, which is what that limit became, is less than 1. And we happen to know that will be true as long as x is between 1 and 3. And you may, just to remind you of your algebra, the absolute value of x minus 2 being less than 1 means that x minus 2 is between 1 and negative 1. Now add 2 to all 3 sides. There you go. So we get that our interval of convergence might be the interval from 1 to 3. The nice thing here is that we know the center is at 2. So I can easily tell you right now the true radius of convergence. It's the distance from the center to either edge. It's the same distance both ways. So I know my radius of convergence here is just 1. A good visual of this right there. And now we have to test the endpoints, and this is where we're starting. I know it took 20 minutes, but the reality is I think it's super important for us to all get caught up and be on the same page. All right. So here we are. We're going to go ahead and test those endpoints. How do you test those endpoints? And really, why? Why do you even bother testing those endpoints? Well, the reason why is because one of those, so you're guaranteed that, for example, if X were 2.5, I know that as long as I add up an infinite number of terms, this series will converge to a finite value. It will not go off to infinity because the radius of the center of this is at 2 and the radius of convergence is 1. So it should converge for anything between 1 and 3. Now we need to say, well, what about at 1 and what about at 3? Will it converge at those edges? So here's how I recommend doing it. Checking endpoints. We have 2 endpoints to our interval of convergence, x equals 1 and x equals 3. If you look at the power series right here, evaluated at x equals 1 and then evaluated at x equals 3, here's what you get. The summation n equals 0 to infinity. At x equals 1, you get 1 minus 2 or negative 1 to the nth power over n squared plus 1. Now, I don't know if you remember me saying it last time because I say things kind of quickly. I completely understand that I run through things sometimes. So let me just reiterate this. When you're dealing with power series, you're often going to use the ratio or the root test. However, when testing endpoints, you'll often use the alternating series test. So you do have to remember your alternating series test, and you can see it right here. But yet again, another however is that you're not only testing the left endpoint, x equals 1, you have to test the right endpoint, x equals 3. So let's go ahead and write down that power series. Let's see, it was 3. We're plugging in for x, so it's 3 minus 2 or 1. 1 to the nth is always just 1. And the denominator is n squared plus 1. You should note the one, this guy right here that I just wrote down, that is the absolute series for this alternating series. This will always be the case. So when you are playing with power series and you need to test endpoints, and I'll write this down in ink in a moment, but I want to say it out loud right now. When you're playing with a power series and you find this interval of convergence, in this case, we found it to be from 1 to 3, and you have to test the endpoints, you will have to test, technically, 2 different series. This one on the left endpoint and the one using the right endpoint. However, we just finished a section, 11.6, which tells us if the series of the absolute or positive terms converges, then your series will converge absolutely. So the series of the alternating terms will also converge. So that's going to be a very powerful theorem to use here, because what I'll want to do is check the non-negative series first, always. I'm going to check this series for convergence. If it converges, I know the alternating series converges. I don't have to check the other side. So I'll write that down as a piece of advice right now. So advice. When checking endpoints, for convergence, comma, you will, whoops, except you don't spell you that way. You will always, well, that was supposed to be blue. It's my way of bolding. You will always end up with an alternating series and its absolute value version. That's what we have here. An alternating series on the left and the absolute value version on the right. The advice here is to test the convergence for the positive or the absolute value version. Test convergence I'll say for the non-alternating version. First. Remember, if the summation of the absolute value of a bunch of terms converges, then the summation of the original one also converges. So thus, I'll just put this in parentheses, which implies alternating version would converge. So always, I think, a great tactic is to always test the non-alternating series first. If it converges, then you got 2 for the price of 1. You've just proven both converge just by proving 1. Now, if it is the case that, by the way, when you go to prove that the non-alternating one, when you go to find the convergence or divergence of the non-alternating series and you find out that it diverges, well, then you just have to test the alternating version separately. So in that case, you will have 2 series to test. But still, I'm okay with risking testing 1 so that I can only test 1, but risking the fact that I might have to test both rather than always testing both. Just test the positive version first. If it converges, both of them will converge. If it diverges, then you also still have to test the alternating one. Okay? So here we go. Let's go ahead and test for convergence of the non-alternating series. And you can easily see the non-alternating series is going to converge because it's a 1 over n squared roughly, but it's not exactly. So I'm just going to go ahead and test. Oops. We know it converges, but I'm just going to do it anyway. Test the summation n equals 0 to infinity of 1 over n squared plus 1. Well, we know n squared plus 1 is greater than n squared. So therefore, 1 over n squared plus 1 is less than 1 over n squared. And we know that the summation 1 over n squared converges by P series test. Thus, the summation 1 over n squared plus 1 converges by series comparison test. Notice that I'm using all my tests previously within this. So it is just, you're going to get a lot of practice with that. That's just how it is. So we found out that the non-alternating series converges. This implies the alternating series converges as well. And there's no real test name for that. It's just that if a series converges absolutely, then the series converges. And so since this series, the absolute values of its terms converge, then that series itself will converge. The alternating series will converge. So therefore, we have convergence at the endpoints. I'm just going to say implies endpoints are included in the interval of convergence. That's what IOC. So our interval of convergence is not this open interval from 1 to 3. It's actually the closed interval from 1 to 3. So whatever this function or whatever function this power series represents, the power series will link to that function from x equals 1 to x equals 3 as long as I add up an infinite number of terms. It won't look like it converges at 1 and 3 for quite some time, because it takes an infinite number of terms for it to actually converge at the edges. The edges are the last piece. This is how I always sorry, there was a question that just came in. Avi, it was 1 to the nth, but what is 1 to the nth? The main x equals 3 series. Yeah, this guy right here, it's 1. That is 1 to the nth upstairs. It's just 1 to the nth power. It's just 1. Right? 1 raised to the nth power is just 1. Yeah. So let's see. Oh, the way I generally think about power series representation, and this might be, let me see if I can find this before. It's dangerous Googling anything live because terrible things can come up. But let's see. Okay, there we go. And let's go to images. And I like this one. Okay, so I'll share my screen here. Share screen. So this is how I think about what I think of power series looks like to me. It always looks like one of those car dealership inflatable men. And the reason why I say that is because if you take a look at a power series, this is the power series we were playing with earlier for e to the x. Okay. Let me bring it back down to 0 here. As you add terms, it wavers back and forth like an inflatable, like one of those car dealership inflatable men. It just keeps wavering back and forth, flipping, right? It does this thing all the time. But as you add more terms, the flipping ends up extending out towards the edges. So it initially, when you only have like 2 terms adding, it flips really close to the center. And then as you add more terms, that edge widens and the flippy little arms get further and further away from the center, or the center. So I've always thought of it that way. I don't know why. It just makes sense to me. And since we're on this page, I might as well just showcase this power series that we just did. So I'm going to go ahead. I'm going to remove this. I don't need this. I'm going to bring this down to 1 for now. And the power series that we were given just a moment ago was x minus 2 raised to the nth over n squared plus 1. And remember, we said that this converges on the interval from 1 to 3. So I'm going to go ahead and maybe adjust this window to go from x equals 0 to 4, just so you can see it really nicely. And I don't need my y-axis to be so crazy. So I'll go from like -5 to 6 or something like that. Okay. Now I'm going to start adding terms to this series. Now you could see it is like one of those flippy guys. As you add more and more terms, it seems to lock in between 1 and 3 there. I mean, it really does. Like it seems between 1 and 3 that it isn't really changing when we add more terms. It's outside of the interval from 1 to 3 that it keeps changing. So if I reduce the number of terms, you'll see outside of that interval from 1 to 3, it's changing. But as you add terms, it seems to be converging to some like nice, clean, sort of concave up curve there. Hard to say. And by the way, we don't know what the function is. So this is the hard thing when you're dealing with power series, is that you want to know, well, what is the series that we're dealing with? And the reality is we don't know. We don't know what that series is. Let me share my screen. Or we don't know what that function is. Sorry, didn't mean to misspeak there. Would the interval of convergence be soft brackets if the series diverges at the edges? Yes. Yeah. I like how you call that. I've never heard of that called soft brackets. The rounded parentheses. Yeah. It is true though. The series would be open interval from 1 to 3 if the power series, turning down my light here, it's just ridiculous. If we didn't, when we check the endpoints, if they didn't have convergence, you would have open intervals at 1 and 3. And we'll see that. I spend a lot of time on this because I just think becoming an expert with this and also feeling comfortable with it is nice. The visuals help out. You start going, oh, well, that's not too terrible. And it isn't. It gets a little wonky after a while, but at least for right now, it's not too terrible. All right, let's step into a different example and see if we can increase our level of knowledge here. So find, again, the same question. Find the interval and radius of convergence for a new power series. It is a power series because it has x in it, right? It's x right here. So it's definitely a function of x. I could even write that, it's f of x. So let's go ahead and use, it's not going to be the root test, even though 2 of the factors are raised to the nth power. That denominator is not raised to the nth power. So the root test is out of the question. So let's try the ratio test. And we'll take the limit as n runs off to infinity of the absolute value of the n plus first term, which is 2 to the n plus 1 over n plus 1. And I'm just going to park that parenthesis in the numerator, times 4x minus 8 to the n plus first power. And now we'll multiply that by the reciprocal. I'll use blue for the reciprocal, by the reciprocal of the original term. So that was n over 2 to the nth times 4x minus 8 raised to the nth. There we go. Very nice. And cleaning this up is critical. So let's go ahead and clean this up as much as possible. This will be the limit as n tends to infinity. I tend to have a bad habit of starting in the middle of my page. I'm going to rope that up and move over. It's the only thing I'm going to miss when going back on ground eventually is being able to move my ink. All right. So let's see. If you start canceling things, we have 2 to the n plus 1 in the numerator. Dividing by 2 to the n, that means we have a 2 in the numerator. We have a 4x minus 8 to the n plus 1 in the numerator, divided by 4x minus 8 to the nth in the denominator, means we have a 4x minus 8 in the numerator. And then we have an n over n plus 1. I can pull out everything that doesn't rely on n, all factors that don't rely on n, I will pull them out. So I get this 2, because that's already positive, times the absolute value of 4x minus 8, times the limit as n goes to infinity of the absolute value of, well, we don't need absolute values on this, n over n plus 1. You don't need absolute values on that because n's going to infinity. Those n's are positive, so nobody cares about that. And that limit is going to be 1. So we have this. Actually, I hope you don't mind. I'm going to factor a 4 out of both these. So we have 8 times the absolute value of x minus 2 is what that simplifies down to. And we want, I'll write this in blue, we want this to be less than 1. Okay. For convergence, remember, the ratio test, for convergence, you require that whatever that limit turns into, you want it to be less than 1 in the long run. So here I'm just saying I want that 8 times x minus 2 absolute value to be less than 1. So we're going to need to solve 8 times the absolute value of x minus 2 is less than 1. Welcome back to algebra. Now, main thing I want you to note here is I normally will start by, I'll normally state the radius of convergence first, because the radius of convergence is the same. Whether you have convergence on the edges or not, the radius of convergence will be static. So you will be able to state the radius of convergence in a moment. But I do want to give you the key to the kingdom here so that you know how to easily state the radius of convergence. The radius of convergence can be found by isolating, I guess, the absolute value of, I'm going to be very clear here, a 1x, except for that 1 is kind of weird to me, plus a, or let's not say a, plus c, less than capital R. This is the radius of convergence. The reason why I write 1x is because if that x, let's just pretend that x had a 3 in front of it. Actually, let me solve this out, and then I'll tell you. So this will imply that we have the absolute value of x minus 2 is less than 1/8. 1/8 is our radius of convergence. That's the radius of convergence for our power series. I happen to know this power series will converge from its center all the way out to 1/8 to the right and 1/8 to the left from the center. Okay. However, if the coefficient of x on this statement right here, and I'm going to go ahead and write this in ink, in red ink, actually. If we had, let's just pretend, the absolute value of 3x minus 2 times 8 is less than 1. If it was like that, we don't have that, but if it was like that, when you divide both sides by 8, you'd get this. This is not the radius of convergence. You have to actually divide everything by 3 as well. So you would factor out a 3 and then divide everything by 3. That would be the radius of convergence. So just a heads up, you want your coefficient of x to be 1 is the punchline. Okay, you just want your coefficient of x to be 1. So we were lucky in this case that the coefficient of x actually was 1, and that gives us the radius of convergence very quickly. But not only that, it also gives you the center. So a lot of people will look at this original power series up above, or all the ink is on the same page now. A lot of people will look at that original power series and they'll say the center is 8 because it's something minus 8 to the nth power. And remember, when we defined the center of our power series, it was x minus a to the nth, right? And so a lot of people will say, oh, well, if it was 4x minus 8 to the nth, then 8 must be the center. But that's not true, because note, this is 1x, not 4x, but 1x. So everything's about, everything with power series requires the coefficient of x to be a 1. So this is not, let me just make that mention here. This is not the center. You can only find the center once you have factored out that lead coefficient. And that's usually done when you are finding the radius of convergence. When you find the radius of convergence, that is this. In fact, I'll use green ink because that means good. That is totally the center. Center is at 2. So we have an interval centered at 2, and we know its radius of convergence is 1/8. So it's 2 plus 1/8 and 2 minus 1/8. We know we're guaranteed convergence, at least on the open interval. We still have to check the endpoints. But we know that that is roughly our interval of convergence. It's our candidate interval of convergence, if you will. Now, I do want to go over to the red ink really quickly and just mention, if you had instead of 8 times the absolute value of x minus 2 is less than 1, if you had 8 times the absolute value of 3x minus 2 being less than 1, remember, you would eventually try to get x to have a lead coefficient of 1 by factoring off that 3 and dividing. And in this case, the center would be 2/3. So no matter what, once you get x with a lead coefficient of 1, you will not only get the radius of convergence, you'll get your center. You almost have everything done. And if you take a look at it in the case that we have over here on the left, we almost have everything done. We just now need to check the edge points. I'm going to write them as actual fractions. So 2 is 16/8 minus 1/8. That's 15/8. And this is 17/8. All right. So once we have found our radius of convergence, let's go ahead and test the endpoints to see if they're included. And no, Veronica is asking, is the center always positive? Great question. No, it is not. So I'm going to put this in blue right here, and I'll just repeat that question. Is the center always positive? And the answer is no. Just consider this. What if it was 2 to the nth over n times, let's just completely change it, 3x plus 6 to the nth. That plus makes a significant difference. That means that center is going to be a negative value. Remember, the center is actually what turns this into 0. What value of x turns that into 0? This is 0. Ink is too thick. When x is 2, implies center is 2. That's a fast way to find the center. Well, I don't want that arrow there. The same idea would happen here. This is 0 when x equals -2. And so in that case, the center is at -2. Yeah. So it is not always going to be the case the center is positive. It could be negative. It just depends upon what turns that factor with x into 0. That's your ultimate goal. How can I turn that factor off? Very fast way to find the center. All right, let's check the endpoints. Check endpoints for convergence, that is. So we have 2 endpoints, x equals 15/8, and then x equals 17/8. You're going to go back to your original power series and plug those values in for x. So our original power series was 2 to the nth over n times the quantity 4x minus 8 to the nth. That looks pretty terrible, right? So we'll just go ahead and do that. That was starting at 1. So we have the summation n equals 1 to infinity of 2 to the nth over n. And then we're going to plug in 15/8 in for x. If you plug in 15/8 in for x, well, that's 15/8 times 4, which is 15 halves. And then you're going to lose 8, which is losing 16 halves. 15 halves minus 16 halves is a -1/2. So I'm going to go ahead and write that. And I'll even write the same thing over here for 17/8. The series again was 2 to the nth over n. And if you try to plug in 17/8 into our original power series, in for x here, 17/8 times 4 is 17 halves, minus 16 halves is a 1/2. Notice One is the non-alternating series and one is its alternating series. It will always end up like that. It's awesome. So go ahead and check the non-alternating series first. If the non-alternating series converges, then the alternating series must converge as well, and you've killed two birds with one stone. You're happy. If the non-alternating series diverges, well, you got extra work. Such is life. All right, so let's go ahead and start here. Start here. Let's clean this up. It's the summation n equals 1 to infinity. I have 2 to the nth over 2 to the nth. That's what these 2 to the nths are. 2 to the nth over 2 to the nth. That's really what that is. So they cancel beautifully, and you get the summation of 1 over n. Well, we know what happens there, right? Yeah. Divergent harmonic series. So because the absolute version diverged, that means that we have to check the other endpoint separately. That's the only, it's not really a bad thing. You'd have to check both endpoints if you had started with the alternating. No matter what, you'd have to check both endpoints had you started with this one. But starting with the non-alternating gives you the chance that you might only have to check once, because if this converges, then the alternating would converge. Unfortunately, this diverges, so oh well. All right, so 17 over 8 is not included. In the interval of convergence, by the way. Now we have to check the other endpoint, because divergence at one end does not imply divergence at the other, unfortunately. And luckily, this does clean up. This is summation n equals 1 to infinity. The 2 to the nth cancel, but you still have a negative 1 to the nth. And that is the alternating harmonic series, and we know that converges. There's no real work there. Alternating harmonic series implies convergence. We've already proven that in the past. So I know that 15 over 8 is included in the interval of convergence. So now we know our actual interval of convergence. Remember, when I wrote this down right here, this was the candidate interval of convergence, but we had to check the endpoints. We just did check the endpoints, and our true interval of convergence is 15/8, including, right, all the way up to 17/8, but not including 17/8. It's one of those wavy arm dudes where on the left edge, his arm clamps down to whatever function we're trying to model. But on the right edge, his arm still wavers quite a bit, no matter how many terms we add up. And by the way, I should state the radius of convergence here cleanly. We had stated it earlier. The radius of convergence is 1/8. So I'll just go ahead and say that. It's basically the distance from center to edge, but there we go. So far with power series, and as far as intervals of convergence and radius of convergence, we've seen infinite intervals of convergence and therefore infinite radius of convergence. We've seen finite or open-ended, let's say open intervals of convergence, right? From an open 1 to an open 3. We've seen closed intervals of convergence. That was the previous example. This guy right here. Closures from 1 to 3. I guess we didn't see the open from 1 to 3, but there's the closure from 1 to 3. And then we've seen half open intervals of convergence from 15/8 to 17/8, not including 17/8. There's one more style that you're going to see. Before I go there, I want to make sure, any questions on this before I leave this page? I'll take a drink and allow you some moments to type in whatever you want to. And you could always, by the way, use Desmos to visualize. It's not super helpful when you don't know what the base function is. So that's what kind of sucks, is that you just don't know what the underlying function is for whatever this power series is. So it's not really going to be super impressive, but at least it does showcase that you have convergence on this interval. And it actually does, in some way, justify what you've done. And maybe I should do that here, because I do want to really get you guys awesome with this stuff. So we're back to Desmos really quickly. And the way you would do it is you just type in a function name. I use g of x, type in the word sum, and it creates the summation sign. We're summing, in this case, we were summing from 1. So let me start at 1, which means I don't want to start this at 0. And we'll go to, I'm calling this A so that I can have a slider for A. That's all. Just when you build a slider in Desmos, make sure that the step size is 1. In other words, it doesn't go through, let's say, 3.7, because it'd be weird to add from 1 to 3.7. That just won't work. And then you type in whatever your sequence term is. And in this case, it was 2 to the nth. So let me just fix that. Over n. And then times, and it was 4x minus 8, and it was to the nth. All right. Now remember, we said the interval of convergence for this was going to be from 15/8 to 17/8. So let me go ahead and show that. X equals 15/8, and I'll also showcase x equals 17/8, just so that we know our boundary here where we're saying it should converge. Now I'll go ahead and start adding up terms. Okay, so it looks as though our curve probably looks like this. And by the way, you'll see Desmos will slow down. It's because Desmos is only a computer and it can only take so much. But this, it looks as though it converges. If I back off a few terms of our summation, I could have already broken Desmos, honestly. There we go. You can see that it's definitely linked between 15/8 and 17/8. It's that purple curve is just not changing. It's because it's already converged. It's just at the edges that you have that wavering bit. So that's pretty convincing that our power series, we're correct with our interval of convergence with our power series. Maybe not at the endpoints, because it's hard to tell unless you can add to infinity, but at least what we see right now. Right, let me get back to my laptop. Okay, so the last example in this section, I really hope you enjoy this section. I hope that it's something that's making sense so far, because it really is just some beautiful theory. Let's find the radius and interval of convergence for this power series. Now, just looking at this power series, as n gets huge, you better believe n factorial is going to blow up, right? Like n's going to get massive, so n factorial is going to get massive. But not only that, let me see. I'm trying to change something here. Hold on, give me a moment. Whatever. But not only that, then you're taking 2x plus 1 and raising 2 in the nth power. So things get really, really massive in this case. So this might diverge for almost every value of x. Well, let's go ahead and find out. You're not going to use the root test here because, again, you don't have nth powers on every factor. So again, ratio test. I love this stuff because of the fact that it's the ratio test or the root test. It's just super nice. It's the only time you step out of those is when you're testing endpoints. So the ratio test, again, let me not start all the way on the center there. We'll take the limit as n goes to infinity of the absolute value of the n plus first term and we'll divide it by the nth term. In this case, I will actually just divide it by the nth term because we didn't start with a fraction, so we don't need to multiply by the reciprocal. All right, let's clean this up. The 2x plus 1s, they cancel, except you'll be left with a single power of 2x plus 1 in the numerator, which I will go ahead and factor out. And as far as factorials go, that n plus 1 factorial is n plus 1 times n factorial. And so the n factorials will cancel beautifully. And so we have the limit as n goes to infinity of n plus 1. Now, no matter what x, well, that's not true. For most values of x, this is going to be infinite, right? Because this limit tends to infinity. Here's where the calculus gets fudgy a little bit. When you first walked into a calculus class, your instructor should have told you, I know you think it's true that 0 times anything is 0. And that is true if 0 is a constant and the anything is constant. However, when you're dealing with limits, the limit of something approaching 0 times the limit of something approaching something not 0 is not necessarily 0. It depends on who's going where faster, right? If something's approaching 0 faster than something's going to infinity, then all bets are off. It might tend to 0. In this case, yes, the limit is tending to infinity. So for any value of x, almost any value of x that I plug in, this will be infinite. But there is one value of x that will turn this into 0. What is that value of x? Yes, thank you. When x is equal to a negative 1/2. When x is equal to a negative 1/2, this is identically 0. Not approaching, but is identically 0. It is a static 0. So if you plug in x equals negative 1/2, this will be 0 identically. And you're multiplying something that's approaching infinity, but it's going to infinity, but it's not infinity. It's going to infinity. But 0 times anything that's not basically a static 0 times anything is going to be 0. So in this case, because that 0 is not within a limit, it is 0. It's not approaching, it is 0. And so we know that the only time that that limit is going to be less than 1 is when x is equal to negative 1/2. And I had mentioned this earlier. It was on the second page of the lecture notes here, or maybe the third page actually, that no matter what, we are guaranteed convergence at the center. We're always guaranteed convergence at the center. And this is that case. If you take a look at our power series here, ask yourself, what would turn that into 0? Well, negative 1/2. So I'm guaranteed, no matter what, before I even start doing calculus, I know this will be convergent at x equals negative 1/2. Otherwise, we've just found out the limit via the ratio test will be infinite, which means it diverges everywhere else. So the interval of convergence and the radius of convergence. Well, the radius of convergence is 0. There is no radius. It literally only converges at its center. Everywhere else, it diverges. It's the wild, wacky car dealership inflatable dude. The interval of convergence is not actually an interval. It's a single point. It's the center. I use roster notation for that to indicate it's just a single point in space. So that happens very quickly, but I just want to make sure you saw that. Let me showcase this on Desmos, and then I'll come back to the screen. So sharing my Desmos, hopping back and forth quite a bit today, but I think that's actually beneficial. I'll reduce this back down to let's just go down to 2 or something like that. Actually, I'll go to 1. The summation was, and I can turn off these edges. There we go. The summation was from 0 to infinity. Okay. And let me actually just erase the entire thing and start over with it. So the sequence was n factorial and then times 2x plus 1 to the nth. Now, I'm going to go ahead and scroll over because x equals negative 1/2 was the center of the series, right? About there. Negative 1/2, comma 1. Actually, let me plot that as a point. Negative 0.5, comma 1. Okay, there's our center of our series. Now watch as I add terms. Notice that as I add more and more terms, the interval over which it looks like it's converging gets smaller and smaller. Give it a moment. I might just have broken Desmos. There we go. So you can see it just keeps shrinking and shrinking. If I go to infinity, which Desmos won't be able to handle, so I'll just stop here. That interval of where it looks like it's converging will suck its way down all the way to the center. So it only converges at its center. It diverges otherwise. And to showcase the divergence, by the way, look, it's wildly an infinite number. Like it just blows up to infinity to the right and down to negative infinity on the left. So it's definitely jumping off to infinities. So this is the crazy car dealership guy. By the way, as I zoom in, I don't know if you could have seen that, but there was a little jaggedness with it. It's because Desmos is a computer, and so it can't actually approximate that curve very well. Kind of neat idea. All right, let me go back to my laptop. All right, so that was all of power series, at least the introduction. Now, the big question is, how can you tell? Okay, so Raj is asking, how can you tell divergence or convergence if you're using only Desmos? You can't. You just can't, because Desmos can't add up that stuff. So there I got, when I added up those terms, I got to 43 and it starts getting real wacky. That is not a proof that the interval of convergence is, or the radius of convergence is 0. It's not a proof of that. It just kind of is convincing because the interval over which it seems to be locking in gets smaller and smaller and smaller, but it's not a proof. The proof actually is this ink right here. So that's a little heads up, but it's really nice to use Desmos to help you visualize what's going on, because the visual of a power series is how the world works. Honestly, if you think about the stock market and trying to predict values and stuff like that, it's done using power series. And so it's to me some beautiful and very applicable stuff. All right, so all we've been able to do with power series so far is determine analytically by hand intervals of convergence and radius or radii of convergence. But if somebody hands me a function, how can I find its power series? Because that's actually going to be critical. Like, I would love it if somebody handed me a function, which they didn't here. They handed me, well, they kind of did. I mean, obviously this is a function of x, but what if they handed me an actual function like x is equal to sine of x, which we talked about last time, but let's just pretend that we didn't. If somebody hands me a function, how in the world can I create a power series out of it? And why would I want to? That's actually a better question. Why would I want to, right? And the big answer to that is for computational purposes, so that you can take derivatives or integrate that function. There are an infinite number of functions you cannot integrate by hand. A simple one is e to the x squared. You cannot integrate that function by hand. However, if you know the power series for e to the x, then you know how to integrate e to the x squared as a polynomial. And so that's why we really want power series in the long run, is so that we can finish our calculus with a bunch of functions that are really challenging to integrate or differentiate. The differentiate, you can actually differentiate pretty much any function, but the integrate is the hard part. So let's go ahead and take a look at the opener to that.